So we're going to keep trying a variety of optimization problems here as we probably get gradually more difficult. In this case, let's imagine that you are a company that manufactures cylindrical containers. So there used to be a company called American Can, maybe there still is. It was a big bidding war for it, I remember, back in the 80s. And if you are making millions and millions of these cans for vegetables or whatever it is, if you can make them a little bit more efficient, obviously that can save your company a lot of money and maybe even do something good for the planet by not wasting material. So cylindrical cans that have a volume of 355 cubic centimeters, what dimensions will use the least amount of material? So what is our goal here? Our goal is to minimize or maximize. What do you think? Our goal is to minimize. Most of these problems can be written in two different ways. In this case, our goal is to minimize the surface area. But you could imagine that this problem had been written in a different way, which is to say, I have a certain amount of surface area for each can. How should I use that surface area to do what? Get the maximum volume. So there's usually two ways to do such a problem. So here I've drawn a cylinder. If we put the usual variables on it, I've got a height and I've got a radius. And our goal is to minimize surface area, so I'm going to call that S. So let's see if we can come up with a formula for the surface area. And by the way, on exams, I always give you any complicated geometrical formulas. So something like this, we would give it to you, but I think we can figure this out here live. We've got a circle on the top. The area of a circle is pi r squared. We've got another circle on the bottom, so that's 2 pi r squared altogether. Then there's the so-called lateral surface area of the cylinder. That's the part that goes around. So you imagine that if I got a cylinder like this, and I cut it, what do I get? A rectangle. What is the area of that rectangle? Well, the height of the rectangle is the same as the height of the original cylinder, and the length of the rectangle is the circumference of the cylinder. So that's h times 2 pi r. So 2 pi r h. So this is the function we would like to optimize, function whose derivative we would like to take. What's the trouble? Same trouble as in the last problem. We've got a function of two variables. We can't do that. We need s as a function of one variable. So there must be some other information, some other constraint that will let us solve for either r or h. Solve for r in terms of h or h in terms of r. So what else do we know? We know the volume. We know that pi r squared h, that's the volume of a cylinder, right? If I've got a cylinder, it's got an area of pi r squared, and I'm just stretching it out, extending it by a factor of h. So the total volume is pi r squared h. What does pi r squared h equal according to our problem? 355. So this is going to let us solve for either r or h and then stick that back into here. So now, as I mentioned in the first problem, most of the time you should spend some time here to decide which variable to isolate, and then that will save you trouble later. So which one do you think? Should we try to solve for h here, or should we try to get r by itself? Which one? And the answer is h. Because if we tried to solve for r, we'd have to take a square root on the other side, and we'd have to plug r in two different places up here. So that's your clue. On the other hand, solving for h, I just get 355 over pi r squared, no square roots involved, and only one place for me to plug it back in up there. It'll work the other way. It'll just be harder. So there's no reason to make things unnecessarily hard here. So now we have s entirely as a function of r. So s of r is 2 pi r squared plus 2 pi r plus 2 pi r times h, which we've just figured out is this. So now we've got s down to just one variable, so now we can sort of forget all about the situation and just do the calculus. As written, what rule will we need to take this derivative? We will need the product rule because of this. But often you can avoid the product rule and the quotient rule in these problems by doing a little simplifying. So here the pi's will cancel, right? And an r from the top will cancel one of the r's on the bottom. So this whole thing will simplify to what? I'll get a 2 times 355 on the top, which is 710. If I cancel the pi, and cancel one of those r's. And in the bottom, I just have an r. So one thing to notice here is that this function itself is already undefined when r is what? When r is 0. Let's think about what r being 0 will mean. I mean, so the fact that s is undefined at 0 means s prime is definitely going to be undefined. If r is 0, that means the radius is 0. That means we have no can. And if we have no can, we're not going to be able to meet this requirement of having a volume of 355. So really, the domain of this function is r greater than 0. R could be very, very small, 0.0001, meaning you're making something very, very narrow and extremely tall, as you can see in the applet, by making r very small. But the domain here is r greater than 0. So we don't have to worry about something bad happening when r is 0. Let's take the derivative. S prime of r, derivative of 2 pi r squared is 4 pi r. Do we need the quotient rule for this? We could, but we don't need it. It'll be a lot easier if we write this as what? 710 r to the negative 1. So what's the derivative of 710 r to the negative 1? Negative 710 r to the negative 2, which is the same as saying 710 over r squared. That's the same thing that you'll get if you use the quotient rule. As noted, this is undefined at 0. We don't have to worry about that because that's not in our domain. So all we have to do is set this equal to 0. And although we usually factor in these problems, in this case, factoring isn't so easy, although it's possible. And if you want to factor out an r or a 2r, go for it. You'll get the same answer. What we don't want to do is do anything that causes us to lose a root, right? So we're not going to do that. I'm just going to move this 710 over r squared to the other side equals 4 pi r. Remember, the dangerous thing that we don't want to do is take this equation and divide by something. So now if I multiply the r squared to that side, I'll get an r cubed. On this side, I'll get 710 over 4 pi. And I think 710 and 4 pi have a common factor of 2. So we could simplify that. As usual, you don't need to simplify, but 355 over 2 pi. And I want to take the cube root to get r. So r is the cube root of 355 over 2 pi. Now we're hoping this is the what? Max or min? We are hoping this is the minimum, because we are trying to minimize the surface area. So let's check. Is this the min? So we do our number line just as usual. I'm going to put here my critical point, cube root of 355 over 2 pi. It would be nice to pick 0 over here, but remember, 0 isn't in the domain. And if I try to plug in 0, the derivative will be undefined. But this number is bigger than 1, so I can plug in 1. And if I get 4 pi times 1, that's around 13, minus 710, that's definitely a negative number. So v is decreasing out there, which is what we're hoping for, because we're looking for a min. And now I can just pick some huge number, 1,000,000. So imagine that r were 1,000,000. That means you have some extremely, extremely wide cylinder that's very, 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 very short. So if r were 1,000,000, this is 4 pi times 1,000,000. That's 13 million or so. 710 over 1,000,000 squared. This is almost 0. This is definitely positive, just like we hoped. So the answer is yes. So it is what we were hoping for. It is the min. And we're trying to find what the optimal dimensions are. So we should so r should be what we just found. Should be the cube root of 355 over 2 pi. And h should be, well, somewhere on the board we must have a formula that gives h in terms of r, and here it is. 355 over pi r squared, this is my r, cube root of 355 over 2 pi all squared. And as usual, you don't need to simplify, so if you want to leave it like that, that's fine. One thing about these problems is that often if you do simplify, it sort of works out to be something nice. So if we do simplify this, I've got a 355 on the top. I've got a cube root squared of 355 on the bottom, meaning I've got 355 to the 1 on the top and 355 to the 2/3 on the bottom, meaning on the top I really have 355 to the 1/3 after we simplify that. And on the bottom, we've got a 2 pi. We've got a pi here, and then a 1 over 2 pi, 1 over 2 pi to the 2/3. And so let's simplify that just a little bit more. 355 to the 1/3. And this is a pi to the 2/3, so this is like a pi to the 1/3 on the bottom. And on the bottom, I've also got this 1/2 to the 2/3. All right, maybe you won't want to simplify so much as I'm doing here. But I think that this is going to come out to be 355 times 4 all over pi, the cube root of that. Because this 1/2 comes to the top, it's being squared. And the 1/3 means that we're taking the cube root of that, and then we've got a pi to the 1/3 on the bottom. In any case, the point of this is that by using calculus, we can really find the dimensions that do minimize this, and that will allow your company to save some money, maybe save a lot of money, and also do some good for the environment.